I say a lot of nonsense. All right. So when doing data analysis for an ELISA, after you complete your ELISA, you're going to get a bunch of numbers from your spectrophotometer, your 96-well spectrophotometer. And those numbers, they are simply amount of color in each well. That's what they are. The 96-well spectrophotometer we have would give you, and typically any 96-well spectrophotometer would give you optical densities. That's a fancy way of saying how much color they have. It would give it to you to 3 decimal places. I can see on your computers, Excel decides to round it up, right? It's there, but it doesn't show it. All you have to do is highlight the cells containing your data, right-click, go under Format Cells, and then click on Number, and increase your decimal points to 3, and just say OK. So select Number, and then increase your decimal points to 3, and just say OK. Now, and as you can see, that makes all of them to 3 decimal points. The other thing I like to do, I like to highlight everything and center. I would like to center my, I don't like them this way, I just like to see them in the middle. And I also like to highlight my labels and make those bold so they can kind of stand out from the actual data points. So nothing fancy, just inputting the data there. Now, the next thing, if you remember for our experiment, we prepared the standards. Do you remember what the top standard was? It was 1,000 picograms per ml. Now, in this example, I have it as 2,000 picograms per ml. So, what I would do is pretty much say for this standard, the 2.800, I know that it has 2,000 picograms per ml of TNF-alpha. Just giving an example. To be exact, in our case, it was 1,000 picograms per ml. And I press Enter. Now, what was the next standard? It was divided by 2, right? So we went down from 1,000 to 500. So in this case, from 2,000, we're going to go down to 1,000. Now, you could do it one by one and put in the number, or you could just press the equal sign, click on the 2,000, and as you can see, it references the cell. It says E6. Now, this is E6. It just references the address of the cell. And then I would divide by 2. So, and it gave me the answer. But here's the thing. I don't want to be doing this for the remaining. So if I click on my 1,000, you look at my cursor, how it's a cross. But if it comes to the corner, how it turns into a slim cross. And just drag everything down, and it automatically does that for you. Now, obviously, in this case, you might say 8 standards is not a big deal. You could divide them yourself. But again, if you can learn the skills and let the machine do the work, it's better for the machine to do the work. Now, you see that we have decimals in some points. The truth of the matter, the ELISA system we have is not accurate down to a decimal point. So you could, again, change it to no decimals, right? Okay? So far, so good? All right. So we have in one column the actual concentrations. We have the optical densities of one standard. Often I get asked, which standard should I use, this one or this one? It all depends on the R-square value, which we will see later on. Now, but before doing that, I want you to pay attention to the negative. And let's remind ourselves, what was the negative for? When you do that experiment, you have a negative. It's basically something that should not have any TNF alpha, right? Should not have any cytokine, whatever you're trying to measure. But let me ask you this. Why doesn't it show us 0? Why does it show color? It's not supposed to have any color, right? Well, the plastic, the reagents you're using, ultimately they give you some color, right? But you want to set that amount of color to 0. So what we do, we average our negatives. So I'm just putting a label there, it's average. To get an average, all you have to do is press the function key. And you would see something that says average. And say OK. Now, the computer is asking you, what would you like me to average? You would click on the arrow facing up, and you would highlight the data points that you would like the computer to average. If you don't want to highlight, you could always put, in this case, is I6 colon I10. Actually, it's I9. If you look at the place where you input the instructions, it says equals average parentheses I6 colon I9. That refers to those 4 cells. Enter and just say OK. So it quickly averages it for me. It says your average value for your negatives is 0.076. Again, instead of just taking one negative, because we have 4 replicates, we simply took the average of those 4 replicates. And now what do you think we're going to do with this 0.076, which is technically our 0? What do you think we should do? Very good. We're going to subtract it from the remaining of our data points. So we can set everything down to 0, right? So I would just highlight my labels. I'm not going to highlight the negative. I basically cut and paste, right? So again, I would use my equal sign. We say equal. I would reference my first data point for my standard. You see when I click on it, it says F6. That's the address of the cell. And I would minus 0.076. Okay? And just press enter. So now it became 2.724. I'm not going to sit down and do it for everybody. I would simply go this way and then go down this way. Now, these guys don't exist, obviously.
Yeah.
You missed it, how I filled it up? Okay, let me just clear everything. Are you okay with how we did the labels? So from here? Yeah. So this is what you do. You highlight what you're interested in copying, and then you right click and you say copy. And then you would go to the place where you want it to go. Let me just get rid of everything. You click on a cell, and then again you right click, and you say paste, and it pops up. Just like you cut and paste, right? Make sense now? Oh, to determine the average? Yeah. So to determine the average is I would like to take the average of all these 4 points, right? So I could do the following. Let me just delete it for now so you see what I did. So this is where my average would pop up in this cell. So I press the function key. One of the functions provided to me is the average. So I just say, okay, I'm telling the computer I would like to average something. Now, the computer is asking me, what would you like to average? So by clicking here and then highlighting what I like to average, it knows. But in case you're wondering, the function is the average, and it's referring to I6 colon I9, which these are the cells from I6, I7, I8, I9. Okay? And just press enter and OK. And it gave me the value. Instead of me sitting down and putting it and then dividing by 4, that's what Excel does. Okay? Now, remember, our job is to deduct from all these guys the negative. So, if you click the cell where you want to see the first result, and then you could put the equal sign, that tells it basically that it's going to do a calculation. I click on 2.800, but you see how the computer is referencing it as F6. It's saying F6. And then what I would do is say minus my negative, which my negative is 0.076. Enter, and it gave me the answer. Okay? Now, I don't want to do this for every single data point. So what do? I just pull it downwards. 2, 3, 4, 5, 6, 7, 8. Oh, nothing happened. Okay. Again. 2, 3, 4, 5, 6, 7, 8. See? It did it for me. Now, I also want to calculate for these guys, for these guys, for these guys, these guys, and these guys. So now I'm going to go sideways. Now, you see what is showing you 0.076 is because there is nothing here, right? So I'm going to clear that. I'm going to clear the contents. Okay? So you see how quickly it minus that 0.076 from everybody else? Because it knows that based on what I did for the first one, it knows what to do for the remaining. Should we do it again? Okay. Now, the computer doesn't know. I need to show it how to do the very first one. And I chose this one. This is my very first one, right? So, all I have to do is press the equal sign. Now, remember, you see the equal sign here? It also shows in this area. I would click on this cell. You see, it knows that that cell has an address called F6. F6. Now, and it knows that that cell has a value, 2.800. But I don't have to put in the value. I just put the address of the cell. The computer knows to go look for that cell and look what's in it. And then I would say minus my average, right? Minus 0.076, which is 0.076. And just say yes. See? Calculate. Now, I don't want to sit down and do for everybody else. So if I click on that cell, you see how the cursor changes from a thick white cross to a thin black cross? You see that? Does yours change? Is that an iPad? Yeah, that's right. Anyway, pull it downwards. 2, 3, 4, 5, 6, 7, 8. It did for the column. I want to go sideways to do the remaining. Now, where I'm getting the negatives is because there is nothing there. So it's 0 minus 0.076. That's why I'm getting negatives. And in this case, it's getting confused with the word average. It's looking at the text and it's trying to minus 0.076. That's why it says, I don't know what to do. So we're going to clear this test. Okay. So far, so good? Now, I'm just going to copy the values of my standards. I'm just going to put them right next to the optical densities of my standard. Now, I would like them everything to be in the middle. I'm a little bit OCD. Okay, so the next thing I would like to do is generate a graph. Remember in the old days we used to take the graph paper? Did you do that? And you would plot it one by one? 21st century, we're going to let Excel do this for us, okay? So, we do have two columns with X and Y values. Here they are. Highlight those two columns, go under Insert. Let me just do an escape. So again, I'm highlighting those two columns. I'm going under Insert, and I'm going to go under Charts. Now, from the charts, there should be one where it looks like dots, and it's called a scatter. So you're going to select the scatter and select this one where no lines are involved. It's just putting the data points on the graph. So click on that. So here it is. You could put it on the side. Okay, now notice on my x-axis I have concentrations. I could actually label them if it makes it easier for you. And my y-axis I have optical densities, right? So far so good? So I'm going to click on one of the data points, and as you can see they all get highlighted. When you click on it, simply right-click and say, I would like you to add a trend line. It's basically, I would like you to draw the best possible line for my data points. Add trend line. Okay, guys? Good? All right. When you add trend line, the computer is asking you, what kind of trend line? In this particular case, it went straight to linear, and that's what we want. Some cases, you would find that a logarithmic scale is a better fit. In this particular case, it's not, because we know from experience that our system, the ranges of concentrations we deal, they give you a nice line. And all you need to do at this point, you could set the intercept at 0, which is basically going to kind of force it to go at 0 in terms of x and y at the end. You're going to ask you to display the equation. You need that equation. The only reason you bother generating this plot is because you need that equation. And then you're going to tell the computer to give you the R-square value. Now, the R-square value is simply how good of a line you have. And when I say how good of a line you have, I could potentially throw something like this, right? Here's one data point, here's one here, and one here. Oh, here's my line. Is that a good line? I generated a line, right? I'm going to base all my conversions based on this line. This is going to have an R-square value of probably 0.5. What you want to have is an R-square value as much as close to 1. But in real life, you're happy with a 0.95. Sometimes even 0.9 is decent. Okay? Good. So here's our equation. The R-square value is 0.9847. Is that a good R-square value? It's pretty good, you know. I would have been concerned if I have data points here, another data point here, another one here, and then I would argue that this is a straight line. But this is not the case. They're not bad. Okay, so we have a decent R-square value. I would say we have a good R-square value, which means we have a good line. Remember, we're going to use this line. In the old days, we used to do this. We say, okay, I have an optical density of 1.5, which means I have a concentration of most likely 1150. That's how we used to do it in the old days, right? But now we have an equation. So all we have to do is solve for x, right? Y is the optical density. We just don't know the x. So this is what we will do. I'm just going to grab my labels. And I would say, the equal sign. I would reference my top standard. That's the very first data point. No, actually, forget about the standard. We're done. Let me just back off. I really don't need the standards now. Let me get rid of them. I'm sorry. So, the first thing we need to find out the actual concentration is the first data sample we have for the untreated, which is basically this one. We want to convert that 0.174 into an actual concentration. So, we're putting the equal sign. We're referencing this cell, this is our Y value, and we're going to divide by what? What do you think we should divide by? We should divide by 0.0014, right? 0.0014. And just say, okay. And it gave me the first concentration. In case you're wondering what I'm doing, basically, this is y equals mx. My b is 0. There is no b. And I'm solving for x. I'm saying x equals y divided by m. Y is the optical densities, which I have, and m is this guy here. That's all I'm doing. Now, here's the beauty of it. Once you calculate this one, all you have to do is autofill the rest. So I'm doing for the 4, and then I'm going sideways to do for the rest. You see how quickly it calculates for every data point what the actual concentration is? You don't have to go one by one and compare it on the graph. And because my system is not accurate down to a decimal point, I'm just going to say format, and I'm going to say I don't want any decimal points. And just say okay. Yes.
Because on the sample paper, the optical is on the x-axis rather than the y.
Yeah, if that's the case, just solve directly. If y is where your concentrations are, solve for y. So that's a very good point. Occasionally, when your computer plots it, instead of having the optical densities on the y-axis, it might put it on the x-axis and put your concentrations on the y-axis. In that case, you won't be solving for x, you'll be solving for y. It's still the same thing. Actually, it would be even easier. In that case, you would multiply by the m. You would multiply by the credit. So you're not going to divide. So just be aware of that. So pay attention what's on each axis. So you would know whether you're going to be dividing or multiplying. Again, you're still going to be using the ymx plus b. Okay? All right. So far, so good? It's a useful thing. Yes. Yeah, so I simply highlight and I right click and I say format the cells, number, and my decimal places I set it to 0. You know why we're doing this, right? Because our system is not sensitive down to a decimal. I highly doubt it's even sensitive down to 1 picogram. So ideally, we should be rounding to the nearest 10. We don't want to give the false impression that we're actually determining concentrations to 803. It's probably around 800. Okay? And if you look at your standard at around 31 picograms, basically you're down to 0. You're 0.004. That shows you the capability of your ELISA system. I mean, not to underestimate the thing. We're talking about picograms here. It's very, very sensitive. But obviously it's not sensitive down to 1 picogram. All right, so far so good? You might have to watch the video on Blackboard again and see how I do each step. Beautiful. Now, okay, we converted everything. Now we know exactly what are the concentrations for our samples, right? What we like to do, instead of just looking the numbers, we would like to average them. We would like to see the standard deviation within each sample, to see how much they vary within each treatment. And also we would do some statistical significance tests. So what do I mean by that? I'm going to grab my labels again. I don't want to be getting confused, so I always put my labels. So the first thing I like to do is to find the average. I want to find the average. Not that hard to find the average, right? So I would like to find the average from my 4 data points. So I can press the function key. I can say average. I can say OK. The computer is asking me, what would you like me to average? I click on the arrow facing up, and I simply highlight the data points that I would like to get an average. And I just say OK. And before you know it, it gave me the average. So the average for those data points is 112. I would like the average for the remaining treatments. And here they are. I'm just going to center them. Okay? So this is the one thing I did. So far, so good? Now, the next thing I'd like to do is generate what's referred to as the standard deviation, which it gives you basically an idea of how variable each data point is within the average. So I'm going to say I want to calculate the standard deviation, just labeling it. Now, does anybody know the formula for the standard deviation? You don't need to know the formula for the standard deviation. All you have to do is press the function key and say, give me the standard deviation. I'm using the standard deviation P. They come in flavors, but if yours just has standard deviation, select that one. Say OK. And again, the computer is asking me which data points would you like me to find for you the standard deviation. So just click on the arrow and highlight your 4 data points on the untreated and just say OK. So it calculated for me the standard deviation just for the untreated. I would like it to calculate the standard deviation for the remaining treatments. And I'm going to just get rid of the decimals. Good. I'm making progress, right? I have averages, I have standard deviations. Not bad. Now, look at the numbers. The numbers, they tend to be not so pleasant to the eyes, right? What am I interested to see? I would like to compare, for example, my untreated versus my 100 nanograms. Or maybe my untreated versus my 10 nanograms. Is any a figure in terms of what? Yeah, because it allows you to select different flavors of standard deviation, but it's probably close to it, right? You got 38? Okay, don't worry about it, because I selected standard deviation P, which, yeah, I think if you select P, but it's not a big deal. Don't worry about it. Yes. I'm sorry. Can you say? The top chart. This one? This one? Yes. Remember, though we basically took the optical densities, that's what we have, that's what the machine gave us, and we converted them based on our standard curve into actual concentrations. So we used that equation, the YMX, and we solved for Y, because we actually solved for X, because at the bottom the X is what corresponds to actual concentrations. So in the old days, we used to do this. We say, okay, you have an optical density of 1.5. Let me draw a line and then come down this. And I know you have probably 1100. You don't have to do this. As long as you're using the equation of your standard curve, that's what you do. And that's what I did here. I went in there. I referenced my 0.174, which is H16 in this case. And then I divided by 0.0014. Look at the 0.0014. That's my M value. That's what I did. And I only did it for once, and then I autofilled the rest. That's the beauty of Excel. You don't have to do it for everybody, right? I'm sorry? Your Y is what? Yeah. Sometimes it can be different, but is it what the concentration does it give you? Oh, so you do get a B. So in your case, it's giving you YMX plus B. So so you have to minus you're solving for X. You have to minus your B. So in your case, what you would do is say you're still solving for X. You're going to say Y minus B. Put the whole thing in a bracket and divide by M. Now, the reason you're getting a B value, when you generated the plot, did you set the y-intercept at 0? Was it giving you that option? It didn't give you that option, okay. So if it's not giving you that option, make sure you minus the B. I mean, is your B a negative or a positive number? So it's going to be a minus when it goes on the other side. So that's the only reason you're getting slightly different. I wouldn't say slightly, it's probably significant. Yeah. Because you no longer have what I had, which was YMX. My system is YMX. Yours is YMX plus B. All right. It is interesting, isn't it? I mean, it's not just applicable to doing an ELISA. You could use it to analyze data. You're using the machine to do the work for you. All right. So what I would like to do at this point, I don't like to see numbers. I would like to see a bar, you know. It's easier to the eyes. So I'm going to ask the computer to give me a bar chart. And as long as you highlight your labels and the actual averages of each treatment, and you go under Insert, it should give you the ability. You see how quickly it does it? Beautiful. Now, and you could label your chart, you know, change it and say, okay, this is a TNF alpha ELISA. I would definitely label my y-axis. Your y-axis, in this case, you say picograms per ml. You want to label your graph to someone who just sees for the first time. They know what they're doing. But often, people do statistics to confirm statistical significance. So my question to you, if you compare your untreated to the 100 nanograms per ml of LPS, do you see a difference? Okay. So just by looking at it, right? But it turns out that it wouldn't be as straightforward as this one. In general, when you're plotting a bar chart, you want to show either standard errors or standard deviation. You want to plot them, right? You see how much variability? If, I'm just making an assumption here, if my sample had standard errors this big, this wouldn't be a good thing. Yours is popping up as series? To do what? On this one?
Yeah.
Did you do this?
Yeah.
Now, do you have here 100 or 100 ng/ml? Okay. The computer gets confused. If it looks at the number 100, it's thinking it's an actual data value. So you want to put 100 nanograms per ml. So once you put some text, it knows that that's just a label. It's not really a number. Computers are fast, but they're not very smart. All right. So let's put the standard errors. In this particular case, we're putting the standard deviations on the actual bars. So how do we do that? If you click on any of the bars and you go under Design, do you have Design on yours? And slowly scroll all the way to the left in the upper corner and click on Add Chart Element. And slowly scroll down to where it says Error Bars. The error bars would give you a sub-menu, and I want you to select more error bar options. and click on the more error bar options. On your right hand side, I want you to go all the way to the end and say, I want to do a custom one. I want to tell it which are my standard deviations, my standard errors. And you say specify. Click on the specify. Now it's asking you, where are those standard deviations you want me to put on your bars? Click on the arrow and highlight your standard deviations. And just press on the X and do the same thing for the negative. Positive or negative is the same thing. And then highlight it again. Click on the X and just say OK. You see how it puts it there now? You see how they popped up? You see my error bars? All right. So my question to you is the following.
Professor.
Yes. Which one? Oh, how do you get the standard deviation? Okay. Let's see if we can delete them. Okay. So no error bars. Click on any of the bars. Then go under Design and then scroll all the way to the left side where it says Add Chart Element. A menu pops up, say I want error bars, but I want more error bar options. When you do that, on the other side, at least in my system, it gives you an option to custom. In other words, you're telling it where your standard errors are. And you say, I want to specify the value. Click on the specify the value. And now it's asking you, since you want to specify, why don't you show me where they are? So click on the arrow and just highlight your standard deviations for your 4 treatments. Typically, for an error bar, you have a positive and a negative from your average. So you're going to do the same thing for your negative. You're going to use exactly the same standard deviation that you use for your positive. So you're basically highlighting it again. And just say OK. And it pops up. Okay? Now, do you think, so let's give you a real life example. Untreated is, so I have 2 groups of patients. Untreated, I gave them a placebo, sugar pill. The 100 nanograms, I gave them, let's say, 100 nanograms of an Advil. They all had headaches. And I guess the bar shows how happy they are afterwards. Now, in this case, it's pretty straightforward. The people who got the pill, they're happier. It should have been no headache, but you get the idea. Now, if my standard deviation was like this, what does it mean? I have people, even in the group that I gave them the Advil, they're still unhappy. They still have a headache. So in this case, I'm left to wonder if it makes a difference. So usually when you have huge standard error bars overlapping with the standard error bars of the other treatment, you're in a questionable area in terms of whether your pill works or not. So how can we rectify this situation? Remember, when you're dealing with humans, you're going to see a lot of variability. So how can you rectify that? There is something called the p-value. You heard of that before? P-value? It's essentially a probability that what you're seeing is pure luck and what you're seeing is not pure luck. How many of you took statistics? Okay, remember that it's acceptable in the statistics community that if you have a p-value of less than 0.05, that basically what you're saying is likely true. That's basically the cutoff, 0.05. Now, you could get p-values using a variety of statistical tools. We're going to use something called a student t-test. It has a history, this student t-test. The person who came up with it, he didn't want to put his name, so he put it as a student did. Apparently he was afraid of what the results would show at the time. But anyway, it's one of the simplest ways to test for statistical significance. And what do I mean by statistical significance? In our case, if I give the cells 100 nanograms of LPS, do they make more TNF-alpha? That's a question. Between you and me, I know it makes them make more TNF-alpha. But let's assume that this was a drug which I didn't know what the behavior is. You getting it? So, I'm going to ask my computer to do a t-test. So I'm going to go under my function key. And I'm going to select something called t-test. If you can't find it, click under statistical and then scroll all the way down till you find T. So here it is, t-test. And select OK. Alright, so the computer now wants me to answer 4 questions. The first 2 are really simple. The computer, as I said, is not very smart. The computer needs directions. The computer is very fast. So what it's asking me to do is this. Which 2 populations would you like me to compare? In this case, it's calling them array 1 and array 2. So I'm going to say my first population is this one, untreated. Okay? And the other one I want to compare it to is the 100 nanograms of LPS. And I say, okay, good. So at least now my computer knows I'm comparing untreated versus 100 nanograms. Now it's asking me for the tails. If you know which way the drug is supposed to push, meaning, is it supposed to make more TNF-alpha? If you do know ahead of the time, in that case, your tail distribution would be 1. Assuming we don't know. Maybe I give them the drug and they make even less TNF-alpha. So if I don't know which way it's going, in that case, I would just put 2. And the last question I would answer is the type. This question refers to the variance. Even though I didn't calculate the variance, looking at my standard deviations, I see that they are different from one treatment to the other. So I'm going to select the unequal variance, which is basically number 3. It's describing here. Is your 2 sample equal variance? Then put 2. Is it unequal variance? Then put 3. It's a little bit overkilling it, but you get the idea. Okay, and it gave me a value of 0.0053. So let me just delete it and I will repeat it so you see what I did. So I want my p-value, I'm going to type here p-value so I know what it is. And this is where I want to get the actual p-value. So I'm going to press the function key. I don't see my t-test here. So I wonder if I type just t, if it's going to see it. Oh, you know what? If you did it once, just say most recently used, because I used it before. Just select t-test. Say OK. And again, the computer is asking me, okay, you want me to do a t-test, I need 4 pieces of information. The first 2, show me the 2 groups. Okay. Click on the arrow, untreat it. Click on the other arrow, 100 nanograms. I'm done. Do I know which way it's going? I'm going to assume I don't know. So I'm going to put 2. Is my variance equal? It's unequal. I'm going to put 3. Say OK. So it gave me this very small number, 0.0005. 3. It basically means that there's about 53 chances out of 100,000 that they're not different. But there is a 99,947 chances that they're different. In other words, when you give them the LPS, they make more TNFi. Is that a good possibility? Is that statistically significant? It is, right? Right? If it was a game and I had the chances of only 53 out of 100,000 to win, I wouldn't play it. I would play to lose. I have more chances to lose. So that's what it shows. It turns out when statisticians do that, they would do something like this. They would draw a line and they would say, okay, I'm comparing these 2 populations. And they would start putting stars. If you see 1 star, the p-value is 0.05. If you see 2 stars, the p-value is 0.005. If you're seeing 3 stars, it's 0.0005. So in plain English, the more stars, the more convincing you are. That's the idea. But I always say, do I really need the statistics? I just look at it and I can tell you it's different. So there is a saying in statistics that statistics are done right on the spot. You just look at them. Don't they look different? I mean, look at the other ones over there, the other ones over there. But that's how you statistically prove if something is different or not. Okay, so do you get the idea? You get a rough idea? I'm gonna save this.